Our work is titled Sequential Detection of Techniques for Machine Degradation Monitoring. Our research is motivated by health monitoring of machines in a network factory in the Industry 4.0 setting. Here, sensors placed on machinery monitoring different health parameters such as vibration, temperature, acoustic information, and so on, send their sensory information over a network to a central controller. This network could be congested and lossy, resulting in loss of information or delayed information at the central controller. This central controller is the one that makes decisions regarding health of the machines using this sensory data. In our work, we hope to design algorithms for detection of incipient, that is early faults in machinery, which are network aware, have low latency of detection under a constraint on the false alarm level, and have low complexity of implementation. Specifically, we focus on the early detection of defects in rolling element bearing faults. This is because rolling element bearing faults contribute to over 40 to 50% of defects in machinery. We focus on the online detection of defects using sequential algorithms. These algorithms use vibration signals using unobstructive sensing. The literature on bearing defect detection is very vast and has been there for a long time. However, there are some gaps in this literature that existing techniques, which are online, typically used fixed window of samples. This does not use accumulated information over time, and such measures are hence less robust to noise. On the other hand, techniques which have higher detection power are hard to implement in an online manner. Through our work, we hope to bridge these two gaps. A quick primer on vibration signals. Mechanical vibration signals of bearings undergo a change in spectrum or after the onset of defects. Here on the left side, you see the progression of the RMS value of the bearing vibration signal that progressively increases after the defect has set in. On the right-hand side, we plot the power spectrum first during normal operation, then at a time that is close to the defect formation. We see that the spectrum has changed here. Further, we then plot the power spectrum when the bearing has undergone extended degradation. Here we see that the spectrum is somewhat discrete and sparse. Using these, we can note that there are some characteristic frequencies that are sounded when a bearing undergoes a defect. These frequencies depend upon the geometry of the bearing and where the fault has occurred. Also, we have noticed that the vibration signals have extremely low SNR. And so our problem is challenging. To solve this, we model the vibration, some parameters of the vibration signals using parametric statistical models. We assume that before the defect has occurred, that is pre-change, these parameters of the vibration signals are known. This is a valid assumption because a machine typically operates in a non-defect state for a very long time, and any such parameters can be estimated to a high degree of accuracy. Post-defect, that is post-change, the parameters are assumed to be unknown. This is again is a practical assumption because the parameters might get into an unknown state and depends on how the defect has occurred. We then pose this as a non-Bayesian parametric composite quickest change detection problem under the Minimax framework of Lorden-Spraper paper. We want to minimize the worst case average delay to detection under a constraint on the false alarm. The false alarm is measured by a quantity known as average run length to false alarm. This average run length to false alarm is the average time that the algorithm will wait before it flags a defect, even though there is none. So we want to keep this as high as possible. Now, it is known from the existing literature that the GLR-QSUM algorithm is very useful for composite quickest change detection problems. However, the GLR-QSUM suffers from a low ARN to false alarm, although it achieves an average delay detection equal to that of a full knowledge QSUM, that is a situation where both the pre-change and the post-change parameters are fully known. Also, the GLR-QSUM algorithm has a very high complexity of implementation and therefore is not practical to implement in regular day-to-day practice. Towards this, These are our contributions with regards to developing a sequential algorithm. We propose a suboptimal algorithm based on the GLRQSum. This algorithm trades off a slight loss in the average delay to detection performance by ensuring that the average run length to false alarm is of the order of the full knowledge QSum. The loss in the performance in the average delay detection is user configurable. That is, the user can decide how much loss in ADD he is ready to endure, and this, of course, results in some loss in the average run to false alarm. Further, our algorithm has a low complexity of implementation and hence can be implemented in an online manner. We provide performance analysis of the algorithm by providing bounds on the asymptotic ARL to F false alarm using a novel proof technique. We provide bounds on the asymptotic average delay detection and provide an explicit construction, what we call the grid set, for if the parametric distribution is an exponential distribution. Towards bearing diagnostics, we provide statistical models for some parameters of the first and second order spectral characteristics of vibration signals. And then we provide two online sequential detection algorithms, one each using the first and the second order spectral characteristics for the detection of the bearing defects using vibration signals. We then compare the performance of these algorithms using synthetic data and using actual bearing vibration data from popular data sets in literature. And we see that our algorithms actually perform much better than the existing algorithms in literature. And we also extend our algorithms to include multiple data streams. That is, there could be multiple such data streams coming from a single bearing, and we also cover that instance using our algorithms. Thank you.